or we started discussing about different standard signals. First thing that we saw was a very important signal called impulse signal. Okay, we can call number one unit impulse signal. We defined the impulse signal. The definition had two parts. Number one is that if you write the value of delta of t, it is 0 for t not equal to 0, and it is undefined. It is undefined where when t is equal to 0. So that is one part of the definition. This is not complete. Okay, this is only one part of the definition. Second part is important, very important. So delta of t, if you integrate from minus infinity to plus infinity, then you get 1. So together makes it the definition of unit impulse function. Okay, now the second function that we looked at was unit step function. Unit step, you can say signal also, because signals are basically functions. So what is unit step function? So unit step function, you can define it in this manner: u of t is equal to 0 for t less than 0 and 1 for t greater than or equal to 0. Okay, even for t equal to 0 also you can say that it is 1. And then what we showed is that if you take u of t and differentiate it, du of t by dt, if you differentiate the unit step signal, then we get delta of t. Okay, so this is the relationship between the two signals that we have seen. Okay, another thing that we have seen is the sampling property of the impulse signal. That was basically if you take delta of t, multiply it with some function f of t, and then integrate from minus infinity to plus infinity, it will basically sample the value of f of t where you have non-zero value for impulse function, that is at t equal to 0. So therefore this will give you f of 0. Now this can also be generalized by shifting the position of the impulse function, in which case we will have t minus tau into f of t dt, and this is basically going to give you f of tau. Okay, so this is called the sampling property of the impulse function. Now impulse function has various properties, so this is one of the very important property of the impulse function. So we saw two standard signal, unit impulse signal, and we saw their definition. Then we saw unit step signal, and then we also saw the connection between the two, and also the sampling property. So this is called the sampling property. Now impulse function has various other properties. Which also we can have a look at. If you take, so let me just list out properties of impulse function. Okay, so first thing that we saw is sampling property, that we already saw. And number two, if you take delta of minus t, and you can show that it is equal to delta of t, and this means that impulse function is an even function. So how do we show this? So again, most of these properties, in order to prove it, we have to go to the integral definition of the impulse function. So we know, okay, so let's take this function LHS, okay, integrating LHS, what we will get? Integral from minus infinity to plus infinity delta of minus t dt. Okay, now what is this? How to find out this? We do not know what this is, because we only know integral of delta of t dt, that we know that it is 1. So how can we convert this given integral into a form which we know about? So that is done by variable transformation. So what you need to do is put minus t is equal to, say, u, and then therefore t is equal to minus u, and when t is equal to minus infinity, we have when t is equal to minus infinity, we have u is equal to plus infinity. When t is equal to plus infinity, we have u is equal to minus infinity. And not only that, we can say that dt is equal to minus du. Okay, so whenever we do a variable transformation in an integral, what we need to do is that we need to replace wherever that variable comes with a new variable, and dt, that is the differential, should also be replaced in terms of the new variable. And then third thing is the limit, okay, the lower limit as well as the upper limit, you need to find out in terms of the new variable. Okay, so if you do that, for example, when t equal to minus infinity, we saw that u is plus infinity, so put it there, and then t is equal to plus infinity, you know that it is minus infinity. Okay, and delta of minus t, okay, minus t is what? Delta of u. So delta of u. So this is the reason why we did the variable transformation. We want to bring it into the familiar form. And then dt is what? dt is minus du. Okay, so that is what we get. So now this minus sign, you can take it outside. Okay, and then we have something, okay, so this is minus plus infinity, but now this is plus infinity to minus infinity, delta of u du. But you know that the limits can be interchanged by absorbing this minus sign, so that if you do, this will be equal to minus infinity plus infinity delta of u du, and u is just a integration variable, and if you do this integration, what we are going to get? You are going to get 1. Okay, now if you compare the integral that we started with before variable transformation, you can actually change the variable from minus infinity to plus infinity delta of t. Okay, just replace u with t, that we can do because u is a variable of integration. Finally, we put the values for t, and the t or u, whatever variable that you use, it will not appear in the final result because it is a definite integral. Okay, so now if I compare this expression with this expression, that is the starting expression with the final expression, only thing difference that you see is that if you look at here, this is delta of minus t, and here it is delta of t. Everything else remain the same. Okay, so therefore we have proved. Okay, so therefore we can say that delta of minus t is equal to delta of t. Okay, so this is the proof of to show that thus we showed that delta of t is, that is unit impulse function, is an even function. Okay, all right, so now so two properties. Sampling property is what? We multiply the function f of t with delta of t and integrate from minus infinity to plus infinity dt. We get f of 0. I think I have proved this in the last class. Okay, this you can generalize also. Okay, now what is third property? Okay, the third property is find t delta of t. What is t delta of t? Now if you look at these two function, so it is a product of two function, and you will see that it is equal to 0. Okay, and the reason is that delta of t is 0 for all values of time except t equal to 0. And the other function t, if you look at how do you plot t, t is basically a straight line, right, passing through the origin with a slope equal to +1. Okay, so this is say this is x of t, and this is x of t is equal to t. Okay, and this is your t. So everywhere whatever is the value of t, this is 1, and then the function will have the value equal to 1. If it is 2, then the function will also have value equal to 2. Okay, if it is -1, then the function will also have -1. So this is basically t, and it is equal to 0 where at t equal to 0. So when t is 0, the function t is also, x of t equal to t is also 0. So it is 0 only at here, all other places it is non-zero, but delta of t is 0 everywhere except at t equal to 0. So therefore the product is 0 everywhere. So this is just by inference, you don't need to prove explicitly, but you can see that the nature of two functions is such that one is non-zero only at t equal to 0, whereas the other is 0 only at t equal to 0. Okay, so this is t and this is delta of t. So therefore when you multiply, 0 will be multiplied everywhere. Okay, right, so that is number 3. Number 4, find or show that, so these are properties, so I will just write them as a equation. The next property is that delta of AT is equal to 1 by modulus A delta of t. So this proof you need to be little more careful. Again, we can take the integration property or the integration part of the definition of delta impulse unit impulse function, and then you can prove this. Okay, so let's do that. So if I integrate the LHS, integrating LHS, okay, so that is integral minus infinity to plus infinity delta of AT dt. Okay, and I do not know what is this equal to. Okay, so what can I do? I can again do the variable transformation. Okay, so the variable transformation I will do is, now I will take, let AT is equal to u. So what is t? T is u by a. And what is dt? Dt is du by a. Now okay, so dt is du by a. And now if if so, let's first of all take a as positive. Okay, we can do this 2 times. One is the case where a is positive, and if a is positive, then when t is equal to minus infinity, this means what about u? So u is going to be a times minus infinity, right? When t, because u is equal to at, and if a is positive and t is plus minus infinity, u is positive quantity multiply minus infinity. So therefore this will also be minus infinity. If t is equal to plus infinity, then u is equal to a times plus infinity. Since a is positive, you have this is equal to plus infinity. So now I have all the quantities that I require, so I can substitute. So first thing, the limits does not change. It is from minus infinity to plus infinity, which is true only for a greater than 0, which is the case that we are considering first. And then I have delta of u, and then dt. Dt is becoming du by a. A is positive. Okay, it's a positive thing. I'm taking a outside, and then or I will not take it outside. I will group it with the delta of u. Okay, so then minus infinity to plus infinity delta of u du. Okay, so now if you consider these 2 things, okay, so the first thing is where we started with that integral. If you compare with the last after the last integral, which is after the transformation, then you can see that the only difference, I can bring back the variable of integration as t, okay, so which is trivial. I just change u with t, so delta of t by a into delta t by a into dt. Okay, so now if I can compare this quantity, the only difference is here. So therefore I can say that when a is positive, so what we got is that delta of at is equal to delta of t by a. That is part 1. Okay, this is only part 1 because we have restricted a to be positive. Okay, so let me call this part 1 of the proof. Now part 2 of the proof, a is less than 0. Now we have slightly different cases. At again we will take it as u, which means that t is equal to u by a, and again dt I will have again du by a. All of that is remaining same. The difference comes in the limit. So if t is equal to minus infinity, then u is going to be, because u is a into t, so when t is minus infinity, and since a is a negative quantity, so u will go to plus infinity. And similarly, if t is plus infinity, u is going to be minus quantity into plus infinity, so that will be minus infinity. And therefore when you do the integration, okay, so that is, let me do it again, integral delta of at dt from minus infinity to plus infinity. So this is with respect to t. Now I use this above variable transformation, and then with the knowledge that a is a negative number, okay, so I will get basically plus infinity to minus infinity. Okay, wherever it was minus infinity, it will become plus infinity, and wherever it was plus infinity, become minus infinity, and delta of u into, and what is dt? dt is du by a. Okay, so that is equal to this. Now a is a negative number. Okay, a is a negative number. Now if I introduce a minus sign explicitly, okay, that is here as well as here, I can introduce a minus sign. Numerator and denominator I am multiplying with minus sign, and then I absorb this minus sign to the limits, okay, so that it will become minus infinity to plus infinity, and delta of u by minus a. So a is a negative number, minus a is a positive number, so therefore I can say this is modulus, or I can say it is minus a itself, and then I put it like this. So this, if I again do simple variable replacement, okay, this is not a transformation, it is just a replacement of the integration variable, delta of t by minus a, where a is negative number, so we get this result. So now if I compare what I started with, okay, this is what I started with and this is what I ended with, so we can see that, so when a is, therefore when a is a negative number, what we have is delta of at is equal to delta of t by minus a. Okay, delta of at is equal to minus a. And similarly, if I put together the previous result, that is when a is positive, delta of at is equal to delta of t a divided by a. Okay, now if I combine these two, okay, if I want to say this two parts of the result into a single result, then I can say that in general, whether a is positive or negative, we can say that delta of t is equal to delta of t divided by modulus a, because modulus a will take care of the sign. When a is negative, modulus will make it positive, because minus a is positive. If a is already positive, then modulus will not do anything, it will just give you the magnitude. Okay, so therefore this is the proof of this particular relationship. Okay, or this is the property of impulse function. Now we have seen impulse function. You can also talk about the derivative of impulse function. Okay, so one more property. So I think how many properties we have seen so far? So 1, 2, then 3, 4. Okay, 4 we have seen. Now 5. Okay, so this is derivatives of impulse function. Okay, so all of these properties are good to know, so that sometimes in doing problems we can use these properties and find the answers. Okay. So what do you mean by derivative? Derivative means this, right? So if you have delta of t, derivative means you do the d by dt of delta of t. Okay. Now how to define this? Okay. Okay. So this usually this function will come in some kind of integration. Derivative impulse function, they don't appear usually standalone. They will come in as a part of some integration. So we will see what it does to a standard or a normal ordinary well-defined function. So multiplying delta of t with f of t, okay, and then integrating from minus infinity to plus infinity dt. So what is the answer for this? Okay, so what are we doing? We are trying to understand what is the derivative of impulse function. So we will understand it by looking at what this function do to a ordinary function. When you multiply with an ordinary function, well-defined function, and then integrate, what does it do? We know that what delta of t does, it will just sample the value of f of t at the location where this impulse comes. But what does the derivative of delta of t do? Okay, so this is our problem, and you can rewrite this problem like this. That is f of t into d by dt of delta of t dt. Okay, this is just a rewriting of whatever is our original expression. And now if you look at, you can use integration by parts. Okay, first function into integral of the second function, f of t into integral of the second function, which is delta of t, and then apply the limit from minus infinity to plus infinity, minus integral of, again limit is from minus infinity to plus infinity, derivative of the first function, that is you can write f dash of t, or you can okay, let's like f dash of t. It is understood that dash correspond to taking df by dt, okay, into derivative of the integral of the second function, which is delta of t dt. Okay, now what is the answer if you apply plus infinity here? Because delta t is going to be 0 at plus infinity, delta of t is 0 at minus infinity, so both the limit is going to be 0. So first term is contributing nothing, it is equal to 0, because both the limits you have delta t function equal to 0. 0 multiplied by whatever is the function value, that is 0. Okay, so then we have minus. Now if I look at the second part, you can apply the sampling property of the delta function. This is delta function multiplying a function, but now the function is not f of t, it is f dash of t. So it will basically sample f dash of t, and that you will get it as f dash of 0. So the answer is that this integral is going to give you the sampled value of the derivative, or this means what? This means minus df by dt where t equals 0. This is what it means. So when I write f dash of 0, what I mean is df by dt I take, and then the value at t equal to 0 I am looking at. Okay, so there is a minus sign here. Now, so that tells us what is the effect of the derivative of an impulse function. So derivative of an impulse function, when you multiply it with an ordinary function, and then when you integrate it what is going to happen is it will sample the derivative of the function that you are multiplying. Okay, so this I can say part A of the result. Now I can extend this to double derivative. Okay, minus infinity to plus infinity. What will be double derivative of impulse function if I multiply with f of t? So same thing you can proceed. Only what you need to do is so you need to do the integration by parts 2 times, and in that case what will happen is that there will be another minus 1 that will come, so it will be minus 1 the whole square, and then what will happen is f double dash of 0. Okay, now this is just a repetition. I am just skipping the steps here. Okay, whatever we did the step here in the first part or the first part of the problem, if you repeat it 2 times, okay, all you need to do because the limit, the first term in the integration by part doesn't give you anything because delta t is 0 at plus infinity and minus infinity, so only you need to take care of the second part, and you need to do that multiple times. Okay, should I need to do it, or you can manage it yourself? Let me know if you want me to do this explicitly. Can somebody respond? Is it okay for you to prove this yourself?
Sir, excuse me, sir.
Yeah.
Sir, how did you land up in the number 2 points, sir, from the first equation?
You have to repeat this 2 times. Okay, if you want, I will do it. Okay, so let me just straight away go to it. Okay, so we have this, right? So if I apply integration by parts, what will happen? I take this as the first function and this as the second function. Okay, so minus infinity to plus infinity. First function is this, and then this is d square delta of t by dt square dt. Okay, now if I apply integration by part, so the first function into, then integral of the second is what? Double derivative. When you integrate, you will get single derivative, right? So that is the first term, minus infinity plus infinity, then minus integral from minus infinity plus infinity. I have f dash of t into d delta of t by dt, and this is dt. So now I did first time, one time I did apply the property, so this will give to 0. Now I will continue one more time. I apply integration by parts. So here already there is a minus 1. Now I have to put this minus 1 here, and then I am applying first function into into integral of the second. Okay, integral of the second is basically delta of t, right? So first function into integral of the second. So now this is from minus infinity to plus infinity, minus integral from minus infinity to plus infinity. Now if I do the integration by parts, here what is the second derivative of f of t, right? Into delta of t dt. Okay, so that is what you will get. Now again, as I told you, here these functions are going to be 0. Okay, just like d by dt of delta t is also 0, delta t is also 0. So therefore upper limit, when you take t equal to infinity, this one part of the product is 0, and for minus infinity also so this will not contribute anything. Now minus into minus, so that is why I put minus 1 the whole square, integral minus infinity to plus infinity f double dash of t into delta of t dt. Now I apply the impulse property or the sampling property of the impulse function. It will sample the value of f double dash of t at t equal to 0. So this is minus 1 square f double dash of 0. That's it. Okay, what does it mean? It means that you take df by or d square f by dt square and put t equal to 0. Is that clear? Is it clear? Any doubt?
Yes, sir.
Okay. So now you see a pattern. So I can extend the result as a number 3 problem. I will not repeat this again. So from minus infinity to plus infinity, if you have nth derivative of Dirac delta function multiplying f of t, okay, so there is a dt here also, dt. So what will you, can you tell me what will be the result? This will be equal to, we are generalizing, okay, we showed it for first derivative and second derivative of impulse function. Now we are showing it for nth derivative. It will be minus 1 raised to n, minus 1 raised to n f nth derivative of 0. Clear? So this is yet another property of impulse function. So we have seen okay, I think I should not. Okay, so we have seen many properties of impulse function. Now any doubts so far?
Sir,
Yeah.
sir, I got one confusion in that minus 1 whole square that you took, sir.
Minus 1 whole square.
Yes.
Yeah.
Yes,
so
sir.
you see,
Sure.
yeah. Okay. There is a minus 1 here, and there is a minus 1 here, right? So I need to multiply minus 1 into minus 1. So which I wrote it as
Yes, sir.
minus.
Yes.
I could have just removed it because it is just plus 1, right? But I kept it
Yes,
so
sir.
that I can use it for generalization purpose. Because
Yes.
whenever you do integration by part one time, there will be a minus sign coming out. So when you do it 2 times, it will be minus 1 raised to 2. If you do it n times, it will be minus 1 raised to n.
Sir, but this expression will continue, sir, forever.
Yeah, this will continue. So it has so you can say that the impulse function, though it is a very unique function, it has infinite number of derivatives possible. Or any derivative exists, and what it does is basically this. When you multiply and integrate, okay, so just like in impulse function, we know about what it does only by multiplying it with a normal function and integrating. Then only you will know what is impulse function. Otherwise, very limited idea we know about it, right? We have only very limited idea, and that is given at the first part of the definition, which says that it is equal to 0 for all values of time except t equal to 0. Okay, so for t not equal to 0, it is 0. So that's the only information we know, but we don't know what is a t equal to 0. But then the second part of the definition gives you some idea. Okay, though we say it is undefined, we have some idea. When you integrate it, it has unit energy inside. Okay, it has some or unit strength inside. Okay, infinity can have so here it is only at one point there is an infinity. The width of the infinity portion is basically 0, negligible. It is infinitesimal, right? We have defined it in the last class by taking various examples. We took some standard function and then we applied limit to it, and we have seen that the function become thinner and taller, right? So preserving the area inside to become unity. So that part of the property of the impulse function is given by the second part of the definition. So together they define. So impulse function is defined with these 2 parts. This is continuous time impulse function. But if you are looking at discrete time impulse function, then this complication doesn't exist. It is very easy. Only at one value it is 1, and often the students confuse between continuous time and discrete time. Okay, so continuous time domain impulse function is a very special function. Okay, it is also called Dirac delta function, and when you integrate it, you get step function. That also I have shown, right? So okay, I hope if it is clear, we can proceed.
Sir,
Yeah,
I have a doubt regarding the sampling property of impulse function.
correct.
So, where if we shifted it by tau,
Ah,
so then the expression landed up into f of tau when we multiply it with normal function.
yes. Right. So let me come back to it. Um, so you are talking about sampling property. Sampling.
Does it basically means shifting of the function, impulse function?
Yes. It is shifting of the function. So sampling property in general, that is a generalized version of the sampling property. Okay. So a sampling property you can just write it like this also: f of t into delta of t dt. You multiply with an ordinary function. Okay, impulse function you multiply with an ordinary function and integrate. So it will pick out the value of the function where the impulse occur. Impulse is occurring at t equal to 0, right?
Yes, sir.
Now if instead of that I generalize it, I have f of t, but now I have to multiply it with the delta of t minus tau dt. Okay, then it is f of tau. Okay, because the impulse is occurring not at t equal to 0, it is occurring at t equal to tau. Okay, if I plot this it will become clear. So this is our time axis. Now delta of t is here, delta of t minus tau is somewhere here. So this is delta of t minus tau, where this impulse is occurring at tau and everywhere else it is 0. So this I can define it as 0 when t not equal to tau, and it is undefined when t is equal to tau. And then I can say second part of the definition. So this is first part of the definition. Second part of the definition is delta of t minus tau integrate from minus infinity to plus infinity dt is equal to 1.
Yes, sir.
Yeah. Okay, so now this property, I think we have proved it. I think maybe I have proved it only for the first case, but we can prove it for the other case also. So if you do that, for example, so what you can see is that this delta function t minus tau, as I have plotted it here, it is 0 everywhere except at t equal to tau. So therefore I can write this function as f of tau into delta of t minus tau, because all other places I am multiplying with 0. So it doesn't matter what is I put here along with, whether if I put f of tau or f of t, after multiplication with 0 it is exactly the same, right? This result has to be the same. Do you agree?
Yes, sir.
Okay.
In that part, I got confused, sir. They have replaced t with tau, sir.
Right.
And
Okay. So
our desired result is that we should get it 0 or 1, sir.
No. You see, this particular function is what I have plotted here. Okay, this is 0 except at t is equal to tau. So everywhere else it is 0. Okay, so therefore if I have to multiply that function with f of t, I can multiply with a constant f of tau also, because that is the only place where it matters, right? Everywhere else it is 0. So whether I multiply with 1 or 2 or 3 in the remaining part, it doesn't matter to this result, because whatever I multiply it with, delta of t minus tau will make it 0 all other places except at t is equal to tau. But t is equal to tau, I need to put the right value, which is what I am putting, f of tau. But f of t could be different in all other places, right? Except at tau, they are different. But since delta of t minus tau is 0 in all those places, we don't need to bother, right? Whether I put f of tau or f of t, doesn't make any difference, right?
Yes, sir.
Yeah. So therefore, now if you look at this, t is the variable of integration, tau is a constant. So f of tau is a constant. So I can pull out my f of tau outside. So this is equal to f of tau into integral minus infinity to delta of t minus tau dt. Now this is what I said in the second part, this part of the definition of the impulse function, shifted impulse function. This is equal to 1. So therefore this is f of tau. Got it?
Yes, sir.
Yeah. Alright, so let's do some problems because you need to really understand the concept of let me open the book and see some problems. Okay, so problems. So number 1. So 1 minus sine 2 pi or sine t, 1 minus sine t into delta of t minus 2 pi is equal to what? Can anybody tell me? What is it equal to? 1 minus sine t into delta of t minus 2 pi. Find the value. Problem is that find the value. Anybody? Anyone? So again, the property of impulse function is that it is 0 except at t equal to 2 pi, right? This function is equal to 0 everywhere except at t is equal to 2 pi. Okay, so you can write it as, that's what just the previous problem or previous property when I proved it, I did. So this t can be replaced by sine 2 pi into delta of t minus 2 pi. Now sine 2 pi is what? Sine 2 pi is 0, right? So sine 2 pi is 0, so you can just put it to 0, and then this is only delta of t minus 2 pi. Okay. Another problem, t cube. So this is from the textbook which I posted. T cube plus 3 delta of t is equal to what? Same problem, means it's very similar. So delta of t is 0 except at t equal to 0. So if you put t equal to 0 here, so t cube doesn't appear, so it will be 3 delta of t. Number 3, then e raised to minus 2t delta of t. Okay, put t equal to 0 and you have e raised to 0, which is 1, so that is delta of t. Simple problems, okay, but you just need to understand the property of delta function. Another one, omega square plus 1 divided by omega square plus 9 into delta of omega minus 1. So where is the location of impulse? Where is the location of impulse? At omega equal to 1, right? It is a shifted impulse, but now it is a function of omega. That's the only difference. So instead of t axis, you have omega axis, and at omega equal to 1, you have the impulse. So everywhere else it is 0. So you can just replace omega with 1. So that will give you 1 plus 1 divided by 1 plus 9, multiplying delta of omega minus 1. Now 1 plus 1 is 2, 2 by 10, that is 1 by 5, delta of omega minus 1. Right?
Yes.
Yeah. So again, so just knowing the property of impulse, you can immediately do these problems. Another one, integral minus infinity to plus infinity. These are all textbook problem. Delta of t e raised to minus j omega t dt. So impulse is occurring at t equal to 0. So it will sample this particular function. Okay, this function will be sampled. So this is basically according to the property, it is j omega into 0. Right?
Yes, sir.
So omega, so if this is e raised to 0, e raised to 0 is 1.
1.
Another one, integral minus infinity to plus infinity, delta of t minus 2 into cos pi t by 4 dt. Where is the location of the impulse?
Yes,
2. Okay, so you put the cos 2 pi by 4, right? Cos 2 pi by 4, which is equal to cos pi by 2, which is equal to 0. Another one, integral minus infinity to plus infinity, e raised to minus this is x minus t delta of 2 minus t dt. Okay, so just like we did yesterday's about transformations. So here there is a impulse function undergoing some transformation. So what is it equal to?
so e equals to minus t.
Yeah. So where is the location of the impulse at t equal to? So you need to first of all try to plot this. Okay, so you can plot by the principles that we learned earlier. So if this is t, your delta of t is this. Okay, then what you need to do is from here t goes to t plus 2, you can transform. Okay, I am using graphical method, and then you will get delta of t plus 2. Okay, t plus 2 is how? It will be here. So this will be at minus 2. It is shifting. T going to t plus 2 means it is shifting left by 2 units. Then next one, I am applying a transformation. T goes to minus t. So what will it do? Whatever is on the left will go to the right. Okay, so this is delta of minus t plus 2, which is basically 2 minus t. Okay, you can also write it as delta of 2 minus t. Both are same. Okay, so now it is easy to see that the impulse is occurring at t equal to 2. Now if impulse is occurring at t equal to 2, then it will sample the value by putting t equal to 2. Right, e raised to minus 2 x minus 2. Clear?
Yes, sir.
Yeah. Another way you can think about is you can so delta of minus t is basically equal to delta of t, right?
Yes, sir.
Yeah, that is one of the property, or even you can see that from this property, this is delta of t by modulus a. So if a is minus 1, it is basically giving you this property. So you can basically write delta of okay, so scaling. Okay, So I mean okay, so that is one thing. Okay, so that is the first step. If you take that as the first step, instead of doing shifting as the first step, I always told you that always when you do graphically, you can safely do by shifting first and then do the other operation later. But if I have to do this one first, then you need to be careful about the shifting. Okay, so we have got delta of minus t, which is basically the same function. Delta of t is equal to delta of minus t. So therefore delta of minus t, if I plot, it will be same as this itself. So this is delta of minus t itself. Okay, so I did one transformation. Now if I want to do the second transformation, how should I do it? Okay, so I should replace t. Okay, so t, so what I need is minus t plus 2, right? This is what I want to get. So what I can do is that I can take this as minus of t minus 2. This way I can write the given expression minus t plus 2, I can write it as delta of minus t minus 2, right? So this means what? Replacing t with the, so here what is the transformation? T becomes, t goes to t minus 2, which is shifting right by 2 units. So if I draw it, so I have delta of minus t here, which is same as delta of t. Then I apply the transformation, t goes to t minus 2, which is basically this. So this is delta of minus t minus 2, which is basically delta of 2 minus t, which is what we want. Is it clear? So both way you can do, but you need to be a little bit careful. You need to do this algebraic manipulation, which I did here. Okay, this algebraic manipulation you have to do. Minus t plus 2, you can write it as delta of minus of t minus 2.
Sir, then by using this above property, delta of minus t equals to delta of t, then directly we can shift this.
Repeat what you said.
So then by using that property, sir, delta of minus t equals to delta of t.
Yes.
So then we directly shifted it to the.
Yeah, but you need to know that you have to shift it to the right. That is my point. You need to know that. So how do you know that? You need to shift it to the right by this step. This step is what is telling you that you need to shift it to the right, because t is replaced with the t minus 2. Okay, if you do t plus 2, you are going to get a wrong result. So whenever you do shift later, you need to know correctly, clearly, whether you need to shift it to the right or left, and number 2, how much you need to shift. Okay, so these two things you need to know. Okay, so but if you do it this way, it is safe. You can be sure that no mistake will happen. Okay, because you are shifting it first, and how much you need to shift, whatever is the other quantity which is here it is plus 2, so I am shifting t plus 2. If it is minus 2, I will shift t minus 2. Okay, any of this way you can do, but only thing is that you need to be careful. If you do the second approach, you need to algebraically do this to see what is the transformation of the t, and then accordingly you shift it. Okay, here t is changing from t minus t to t minus 2. Okay, as I have shown here, but both will give you the same result. So you need, in order to apply the sampling property, you need the location at which impulse happens. That is a point. So to do all this kind of problems, you need to know that. All right, we will stop here. We'll come back after 5 minutes.